Good afternoon, everyone. Myself, Devayani, and I'm giving Prerana gate classes with the subject of fluid mechanics and hydraulic machinery. So, as you know, the fluid mechanics and hydraulic machinery subject was very important, and we have studied this subject in second year, first and second semester. So fluid mechanics, usually in gate exams, this fluid mechanics and hydraulic machinery subject can score nearly 25 to 35% of the marks. So definitely it will be very helps to you to prepare gate classes and to get the score by using these presentations. So coming to the first topic, so today I'm going to give a brief introduction regarding the fluid mechanics, and then I'm going to discuss about the properties of the fluids, and then I'm going to discuss about the impact of jets, the force which was acting on the jets. Then coming to introduction, so as we know, mechanics is a fluid mechanics. Mechanics is nothing but mechanics means in simple manner. Mechanics is study of its body. The body may be a fluid or a gas or a solid, or fluid or solid, whatever. So simply the study of the body is called as the mechanics. So if we study that body, the body like a fluid, then that study of the fluid is called as the fluid mechanics. Simply to study the behavior of the fluids are known as fluid mechanics. So the fluid includes liquids as well as gases also. Fluids includes liquids and gases also. So if we study the behavior of the liquids and gases, then we can call that study as the fluid mechanics. So all these methods related to the fluid mechanics are same as the mechanics of solids only. The solid mechanics of solids like the steel and the wood. So here also the study of the fluid mechanics will also same like the mechanics of solids. And here this fluid mechanics was divided into three branches. First one is the fluid statics, the second one fluid kinematics, and the third one fluid dynamics. Coming to fluid statics means this is the study of fluid at rest condition. Fluid statics means study of fluids at rest condition. Kinematics means this is also study of the fluids, and here the study of behavior of the fluid, the behavior as velocities and accelerations. And while studying this, we don't consider the forces which were acting on it. So if we study the velocities and acceleration of the fluid without considering the forces or energy, then it is called as fluid kinematics. Whereas fluid dynamics, if we consider the forces and the external forces and energy which were acting on the fluid in between the relation of velocities and acceleration, then that study is called as the fluid dynamics. So in kinematics, we don't consider the forces or energy, and in dynamics, we will consider the forces and the different energies which are acting on it. Then coming to fluid, let's discuss what is fluid. So it is defined as a substance which deforms continuously even with a small amount of shear force exerts on it. And it is a solid of a resistance to the force because a very strong intermolecular attraction can be existed in between the fluid particles. Here the both the liquids and gases both are coming under the same category. Let's discuss the difference between liquid and gas. So liquid is defined as it has a definite volume but no shape for or practical purposes. So we are calling it as incompressible material. And here gas has no shape and no volume. So we can call it as a highly compressible material. Whereas the vapor, a vapor is a gas whose temperature and pressure are such that it is very near to the liquid. So vapor is also same as the liquid molecules. So example for this vapor is steam. Then another one is mean free path. So mean free path means the statistical average distance which molecule of the same fluid travel between the collisions is called as the mean free path. Usually this mean free path will be calculated will be used to calculate the velocity of the flowing fluid in open channels. And of course, any fluid can be treated as a continuous medium if the mean free path divided by characteristic length of the flow is less than 1%. So whatever the type of fluid, the fluid may be grease or oil or water or mercury, whatever. If that fluid is having the ratio mean free path by characteristic length of the flow is less than 1%, then it is considered as a continuous medium. Suppose if this value is greater than 1%, then we can call it as a static medium, or else we can call it as a solid body. So simply by taking this average itself, by mean free path by characteristic length of the flow is less than 1%, then we can call that flow, that fluid as a continuous medium. If this percentage is greater than 1%, then we can call it as a static medium. And when a fluid ceases to be continuous medium, the fluid characteristics as density rho, viscosity nu, and pressure B will be changed from one point to another. So example is gases at low pressure will become as the continuous medium. And of course, these fluids are mainly of two types, ideal and real fluids. Ideal fluid, also known as the perfect fluid. Here, ideal fluid is a type of non-viscous, and it is an incompressible fluid. Incompressible fluid is not a media. Incompressible fluid means the density will not change at any point. So non-viscous and incompressible fluids are considered as the ideal fluids, and these fluids are used in mathematical analysis of flow problems. So to calculate the discharge or to calculate the velocity, in those cases you can use these ideal fluids. Then these fluids does not exist in reality. Why? Because the properties are not, property of the fluids are not constant throughout the length of the pipe. So that we can say these fluids, ideal fluids, are not exist in reality. And these fluids does not offer shear resistance when fluid is in motion condition. Well, coming to the real fluid, so real fluids are the actual fluids what we have seen in the rivers. So real fluids possess the properties such as viscosity, surface tension, and compressibility, and which the resistance is offered when they are set in motion. So this is about the different types of fluids. Then coming to the properties of fluids, so the very first property is mass density, and it is denoted with rho. So mass density is defined as it is the ratio of mass per unit volume, and it has the units kg per meter cube. The absolute quantity, that is the mass density, will not change with location. So whatever the place, it is at the riverside or it is at the seaside or it is in oceans also, the quantity, the absolute quantity of the mass density will not change with location. If the pressure increases, then mass density will also increase due to the more number of molecules are forced into the given volume. Hence, if the pressure increases, the density will also increase. Then coming to the second property, specific weight, and it is denoted with gamma. The weight of the substance per unit volume is known as specific weight. It is also represents a force exerted by gravity on a unit volume of the fluid. Hence, the mass density and specific weight of the fluid are related as gamma equals to rho into g. So that is nothing but if the acceleration due to gravity was acts on a substance, then we can calculate the specific weight. Otherwise, we can calculate only the mass density. Here in this formula, gamma equals to rho into g. So g is the acceleration due to gravity, and it has the units Newton per meter cube, and the dimensions are m L power minus 2 T power minus 2. And it is not like the mass density. It is not an absolute quantity. It varies from place to place as of varies with location, primarily latitude and elevation above the mean sea level. The specific weight of the water is 9810 Newton per meter cube. The next property is specific volume. It is denoted with small v, and it is defined as the volume occupied by a unit mass of fluid is known as the specific volume, and the formula is V equals to 1 by rho. Simply, it is a reciprocal of the density. Units are meter cube per kg. So this specific volume is commonly applied for the gases. Then another property of the fluid is specific gravity. It is denoted with G. Specific gravity is defined as it is the ratio of specific weight of your fluid to the specific weight of your standard fluid. Here, suppose if we have to calculate the specific gravity of oil, then we can write this equation as specific weight of the oil is nothing but specific gravity of the oil is nothing but specific weight of the oil by specific weight of the water. Usually, the standard fluid is considered as the water. For liquids, the standard fluid is water at 4 degrees centigrade. For gases, the standard fluid is considered as the hydrogen or air. So the units, it doesn't have any units. Why? Because both in numerator and denominator we have the same parameters. So there is no units for the specific gravity. Usually the specific gravity of the water is 1. The specific gravity of the mercury is 13.6. Since the density of the fluid varies with temperature, the specific gravity must be determined and specified at a particular temperature. Next parameter, next property of the fluid is viscosity. So viscosity is the main property of the fluid and it is a measure of its resistance to shear or angular deformation. It is nothing but a resistance to shear force or the angular deformation. It is a property by virtue of which it offers resistance to the movement of one layer of the fluid over the other adjacent layer. So due to this collision between the particles, the viscosity will take place. So mainly this viscosity will occur on the water due to intermolecular cohesion and due to transfer of molecular momentum, that is interchange between the layers of the fluid. So this viscosity are of two types, kinematic viscosity and dynamic viscosity. So kinematic viscosity is denoted with nu and it is defined as it is the ratio of dynamic viscosity by mass density, that is nu equals to mu by rho. The units of the dynamic viscosity is nothing but in SI units, the dynamic viscosity units are Pascal second or Newton second per meter square, and in CGS the dynamic viscosity units are poise, and 1 poise equals to 0.1 Pascal second. Then coming to the kinematic viscosity, the units of kinematic viscosity is in SI units, it is meter square per second or centimeter square per second or Stokes. Then effect of the temperature and pressure. So coming to the dynamic viscosity, dynamic viscosity is independent of pressure. It won't depend on the pressure. So for liquids, if temperature increases, then viscosity decreases. Because molecular momentum increases and the cohesion will reduce between the particles. Hence, if the temperature increases, then the viscosity will decrease. But whereas kinematic viscosity is definitely depends on the pressure and temperature. Another property of the fluid is vapor pressure. Suppose if we take a closed vessel at a constant temperature, then the liquid molecules will break away from the liquid surface and enter the air space in a vapor state like this. So if we take some amount of water in a vessel, and if we increase the temperature, then the surface of the water molecule will break away from the liquid surface and enter into the air space in a vapor state. So when the air above the liquid surface is saturated with liquid vapor molecules, then the pressure exerted on the liquid surface is called as the vapor pressure. So if these molecules, if the water molecules will become as vapor molecules due to high temperature, then those vapor molecules will exert some pressure on the water and on the vessels. So that pressure exerted by the vapors is called as the vapor pressure. This vapor pressure increases with temperature. The low vapor pressure of mercury makes it very suitable for use in the barometers and other pressure measuring devices to measure the pressure. Then cavitation. So of course cavitation is in this cavitation also we are going to face the vapor bubbles. Hence the cavitation particle, the cavitation property is a sub property of the vapor pressure. This cavitation occurs in a flow system. It dissolved gases carried into a region of high pressure and their subsequent collapse gives rise to the high pressure and which leads to noise and vibrations and erosion. So mainly due to this obstruction of the water due to high pressure, then the cavitation will forms as a vapor molecules. Usually this cavitation occurs in the turbine runners, pump impellers, hydraulic structures like spillways and sluice gates, and then ship propellers. Then another property of the fluid is compressibility. So compressibility is defined as it is a change in volume due to the change in pressure. So it is inversely proportional to the bulk modulus and bulk modulus K. So we can write it as bulk modulus K equals to minus dP by dV by V. Here negative sign indicates a decrease in volume with increase in pressure. So dP is the change in the pressure and dV by V is the change in the volume. So we can say the coefficient of permeability is the reciprocal of the bulk modulus. So we can write it as coefficient of permeability denoted with beta and which can be written as beta equals to 1 by K. Usually for the liquids, the compressibility will be like, since most of the liquids have a comparatively high value of the bulk modulus, the compressibility is close to zero, hence the liquids are considered practically incompressible. The small pressure disturbances travel through the fluid medium at a velocity equal to the velocity of sound, which depends upon the bulk modulus and mass density. Hence, the velocity of the sound C equals to square root of K by rho. Therefore, the compressibility of water is considered in case of water hammer problems. So, due to the sudden closure of valves in pipelines, a high pressure wave is generated, giving rise to the huge increase of the pressure. And due to that one, the compressibility of the water will takes place. And another property of the fluid is surface tension. So surface tension was mainly acts due to the cohesion and adhesion. Cohesion means the force of attraction between the molecules of the same liquid, and adhesion means force of attraction between the molecules of different liquids or between the liquid and molecules and solid boundary. Liquid molecules and solid boundary containing the liquid. A liquid forms an interface with a second liquid or gas, and this liquid air interface behaves like a membrane under the tension. Thus, the surface energy per unit area of interface is called as the surface tension. In other words, the surface tension is defined as if a tensile force was acting on the surface of the water when it is in contact with the gas, then it is called the property of the water molecule is called as surface tension. The tensile force acting on the surface of the water when it is in contact with the gas is called as surface tension. It can also be expressed as linear surface. The force per unit length is the main definition for the surface tension. So units are Newton per meter and the dimensions are m⁻². The surface tension is mainly due to cohesion between the liquid molecules. As the temperature increases, the surface tension decreases due to reduction of the cohesion between the water molecules. And due to cohesion, the surface tension pressure changes occur across the curved surface of liquid jet, droplet, and soap bubble. So if you take a liquid jet, so the liquid jet will increase in liquid jet. It increases in pressure of inside and outside of the liquid jet. So in liquid jet case, the Change in the pressure can be calculated by using the formula as delta P equals to 2 sigma by D. Here sigma is the surface tension in Newton per meter and D is the diameter of the jet in meters or as in mm. Then liquid drop. In case of liquid drop, the surface tension can be calculated by using the formula change in pressure delta P equals to 4 sigma by D. Here D is the diameter of the droplet. Then the final one, soap bubble. So in soap bubble, the surface tension can be calculated by using the formula change in pressure delta P equals to 8 sigma by D, where D is the diameter of the bubble. Then another property is capillarity. Capillarity is the phenomena of rise or fall of a liquid surface relative to the adjacent general level of the liquid in a small diameter tubes. The rise of liquid surface is designated as the capillary rise. The lowering of the water is called lowering of the fluid is called as the capillary depression, and this is mainly causes due to both cohesion and as well as the addition. So the units for this capillarity is centimeter or mm of the liquids. The capillary rise means if the addition was more than the cohesion. For example, the mercury depressive with the convex upward capillary rise or fall. So usually if the interaction between the water and the mercury takes place, then in if the attraction between the water and the mercury takes place, in that case, the usually capillary rise will occur on the water. So for capillary rise, to calculate the capillary rise, the formula is given as H equals to 4 sigma gamma cos theta by gamma D, where H is the capillary rise, sigma is the surface tension, theta is the angle of contact between liquid and boundary. So that will be at this point. Then D is the diameter of the tube. Usually theta will be 0 degrees for water and glass, and theta will be 130 degrees for mercury and glass. And for the tube, the diameter greater than 12 mm, the capillary effects are negligible. Hence, the dia of glass tubes used for measuring pressure, that is manometers and piezometers, etc., should be large enough. So these are the fluid properties. So let's discuss some of the problems related to these fluid properties. Coming to the problem, the water has the surface tension of 0.4 Newton per meter in a 3 mm diameter vertical tube. If the liquid rises 6 mm above the liquid outside the tube, calculate the wetting angle. So they have given surface tension 0.4 Newton per meter, the diameter of the tube 3 mm, and capillary rise H 6 mm. So now we have to calculate the angle made with the glass and liquid. So for that one, we are going to use the formula, that is H equals to 4 sigma cos theta by gamma D. Here they have given H value, gamma value, sigma value and D value. Now we have to find out the theta. So substituting all the values, H is 6 into 10 power minus 3 meters, 4 sigma value 0.4 cos theta by gamma D. Here gamma is in 9810 Newton per meter cube and D is given as 3 mm, that is 0.003 meters. So substituting all the values and simplifying, we get theta as 83 degrees 66 minutes. So another problem is a reservoir of oil has a mass of 825 kg. The reservoir has a volume of 0.917 meter cube. What are the density, specific weight and specific gravity of the oil? So they have given the mass of the oil as 825 kg, and it has the volume 0.917 meter cube. And using these two values, we have to calculate the density, specific weight and specific gravity of the oil. So coming to the density, the formula for density is mass by volume. So they have given both the values. Simply substituting those values, we can get the density as 899.67 kg per meter cube. Then another one, specific weight. So we know that specific weight is mass density into acceleration due to gravity. So we can write it as this value into acceleration due to gravity, that is 9.81. So substituting those values, we get the value as 8825.79 Newton per meter cube. And then specific gravity of the oil, we know that specific gravity of the oil is standard fluid density of the standard fluid by unit weight of the standard fluid by, specific gravity is defined as unit weight of the fluid by unit weight of the standard fluid. Here unit weight of the fluid, here the fluid is oil. So unit weight of the oil is given as 825 by 0.917 into 1000. Then divide 0.917. Then divided by unit weight of the standard fluid. Here standard fluid is water. So the water is having the units 1000. So by substituting those values, we can get the specific gravity of the oil as 0.903. Okay. The next one, next problem. Given M is mass is 80 kgs and acceleration is 10 meter per second square. So using this, we need to find out the force. As we know, the force is having the formula mass into acceleration. Force equal to mass into acceleration. So substituting that 8 into 10, then the force will be 800 newtons. Another problem, the surface tension of water at 20 degrees centigrade is 75 into 10 power minus 3 Newton per meter. The difference in the water surfaces within and outside an open-ended capillary tube of 1 mm internal bore inserted at the water surface would be. So here what we have to calculate, the difference between the water surface within and outside in the open capillary tube. So within the capillary tube and outside the capillary tube, we have to find out the capillary rise. So to calculate the capillary rise, we have the formula 4 sigma cos theta by gamma d. Here theta is not given. Why? Because in this case, theta will be taken as 90 degrees. So cos 90 is nothing but, theta is taken as 0 degrees. Cos theta is, cos 0 degrees is 1. So this will be 4 into, they have given the surface tension 75 into 10 power minus 3 by gamma into d. Gamma is 9810 and d is given as 1 mm. So it will be 0.001. So the capillary rise is 30 mm. Another problem, the oil has the viscosity 0.44 Pascal second and pressure is given as 888 kg per meter cube. And this oil is filled in the space between two parallel plates which are 18 mm apart. The two parallel plates are having the distance 18 mm. The upper plate is moving at a velocity of 4 meter per second. Then what is the shear stress on the plate? So to calculate the shear stress, we are going to use the formula tau equals to mu into du by dy. So for that one, we are going to take the formula as tau equals to 0.44 into here mu into du by dy. Here mu is the 0.44 Pascal second into du by dy. So the velocity is given as 4 meters and dy change in the distance 18 mm. So mu into du by dy. Mu is the viscosity, du is the change in velocity and dy is the change in the distance. So it will, we can, by substituting those values 0.44 into 4 by 0.018 will be considered as by substituting all the values, we can get the shear stress acting on the plate as 97.8 pascals. Another one, the velocity distribution for flow over a plate is given by mu equals to 0.9 y minus y square, where mu is the velocity in meter per second at a distance y meters above the plate. If the dynamic viscosity of the field is 0.9 Newtons second per meter square, then what is the shear stress at 0.2 meter from the boundary? So they have given change in the velocity and the distance, that is du by dy is given as 0.9 minus 12. So we can write it as 0.9 into 2 into, so the distance is given as 0.2 meters. So substituting that we get du by dy as 0.5. And we know the viscosity. So substituting all the values, now we can calculate the shear stress as tau equals to mu into du by dy. Mu is given as 0.9 Newton second per meter square and du by dy is taken as 0.5. So substituting that we can get the shear stress as 0.45 pascals. Another question, which one of the following expression, the height of the rise or fall of a liquid in a capillary tube? So among all this, third one is the correct one. So the formula is 4 sigma cos theta by gamma d. Here they have represent the expression theta as alpha and gamma as a W. Of course, we know that we can express in any manner. So where W is the weight of the liquid, gamma is the alpha is the angle of contact, then sigma is the surface tension. Another question, kinematic viscosity nu is measured by using the formula as mu by rho. Nu equals to mu by rho. Another one, surface tension in fluids is measured in Newton per mm. So surface tension in fluids is measured in Newton per mm. Why? Because the formula surface tension has the formula force per unit length. Force per unit length. So the units will be Newton per mm. Then Pascal in SI units is a unit of stress. Usually the pascals is the unit of stress. Another question, as the temperature is increased, the viscosity of water will be decreased. Definitely, if the temperature decrease, then the cohesion between the particle will reduce, and due to that, the viscosity of the water will reduce. Another question, cavitation is caused due to high pressure. Here the answer is low pressure, but usually the cavitation is causes due to the region of high pressure, but not at the low pressure. Another question, the dynamic viscosity of a fluid is 0.139 kg of second per meter square. If the specific gravity of fluid is 0.95, then its kinematic viscosity is, so kinematic viscosity formula is mu by rho. So we have the specific gravity of the fluid, that is 0.95. So we have the formula for specific gravity of fluid, that is specific gravity of the fluid is equal to mass density of the fluid by mass density of the standard fluid. Mass density of the standard fluid is usually 1 gram per cc or 1000 kg per meter cube. So we can write it as the specific gravity of the, we know specific gravity of the fluid and we know the mass density of the standard fluid, that is 1000 kg per meter cube. So multiplying 0.95 and 1000, we get 950 kg per meter cube as the specific gravity, this is the value of the mass density of the given fluid. So by substituting that value rho, mass density of the given fluid rho, and substituting mu value, that is 0.139, we get kinematic viscosity nu equals to mu by rho as 0.000146 meter square per second. Another one, the intensity of pressure developed by surface tension of 0.0075 kg per meter in a droplet of water is 6 into 10 power minus 3 mm. Then the diameter is, so here we have to calculate intensity of the pressure. So to calculate this pressure, they are given surface tension and diameter of the water molecule. So by substituting those values in the formula, that is P equals to 4 sigma by D for the water droplet. For droplet, we have the formula 4 sigma by D. For soap bubble, the formula is P equal to 8 sigma by D. For a liquid jet, we have the formula P equal to 2 sigma by D. Right? So substituting those values, we can get from the formula of droplet P equal to 4 sigma by D, we can get the value as 0.5 kg per centimeter square. Then another question, an ideal fluid is frictionless and incompressible fluid. So here they asked to find out the dynamic viscosity. So to calculate the dynamic viscosity, they have given the distance and the velocity and the force. So using all these values, we have to calculate the viscosity. So to calculate the viscosity, of course, we are using the formula tau equals to mu into du by dy. So here we have all the values like tau, we have tau value, we have we have dv value, dy value, and we have du value, that is change in the velocity 61, change in the distance 0.0254, and we have the value of tau, the force 0.2 kg per meter square. So substituting all the values in a formula, that is tau equals to mu into du by dy, we can get the value of mu. So the mu value, the dynamic viscosity is 8.328 into 10 power minus 10 kg of second per centimeter square. Another topic, so up to this we have completed this fluid properties. Now we are going to discuss the another chapter, that is impulse momentum equation. So coming to impulse momentum equation, mainly this impulse momentum equation is mainly used to find out the force acting on the pipe bends and the force acting on the pipe flows. So impulse momentum equation is based on the law of conservation of momentum, and it is derived from the Newton's second law of motion. So the equation is applicable to a control volume. So choosing the control volume, the size and shape is arbitrary, coincides with the solid boundary, it can be drawn normal to the flow direction, and it should cut across the supports to include external reactions. Coming to momentum equation. So momentum equation states that the net force acting on a fluid mass is equal to change in the momentum per second in that direction. The net force acting on a fluid mass is equal to change in the momentum per second. So mathematically it can be written as momentum equation F equals to d by dt of m. Here d by dt is the dm by dt is the change in momentum with respect to time. Here m is the momentum. Momentum is nothing but the momentum is the product of mass and velocity. Momentum is the product of mass and velocity. Then impulse momentum equation. So we can, if we take any body, and if that body was moves from one place to another place, then there is a velocity was act in the body. So the velocity at first section and the velocity at second section in all directions, that is in x direction, y direction, and z direction at the first section and second section. Then using all these velocities to calculate this. To calculate the momentum, we are going to take the change in velocity. So to calculate the momentum, we are going to consider all this momentum, all this change in velocities in all directions. So using this one only, we can calculate the impulse momentum equation. So we can write that what is impulse momentum equation? The force acting on the body is equal to change in momentum with respect to time. So we can write it as F into dt equals to change in the momentum. Here m equals to m into v. Of course, mass will not change to a body, but the velocity can change from one place to another place. So to calculate the force, we have to consider change in the velocity, but not the mass. Hence, we are going to take a body and we are going to calculate the change in the velocity from one place to another place in all directions. So it states that the impulse of a force acting on a fluid mass in a short interval of time is equal to the change of momentum in the direction of the force. If the flow is steady and incompressible, then the momentum equation can be written as in x direction fx equals to rho q into v2x minus v1x in x direction, and in y direction force fy equals to rho q into v2y minus v1y in y direction. The term rho qv is the internal force and it is called as the momentum flux. Rho qv is called as the momentum flux. Then momentum correction factor. Of course, this momentum was mainly depends on the velocity, but this velocity is not constant at each and every point. Of course, the velocity will change from one point to another point due to several reasons, due to the pressure, due to temperature, so due to the forces acting on it, so on so. So due to several reasons, the velocity will change from one point to another point. So to overcome that problem and to maintain the constant velocity, we are going to take a momentum correction factor based on the assumption that the velocity of flow at each section is uniform. So based on the assumption, the velocity of flow at each section is uniform, we are going to get a factor that is called as the momentum correction factor. So due to this, the actual momentum flux is always greater than that computed by using the mean velocity of flow. Hence, in order to account for difference, a factor called momentum correction factor is introduced. This momentum correction factor is denoted with beta. So beta can be written as beta equals to 1 by a v square into integral of a of v square dA. If the velocity is uniform, then beta will be 1. Usually for laminar flow, the beta value is 1.33. For turbulent flow, the beta value is 1.02, 1.05. So another topic is impact of jets. So it means the force exerted by the jet on a plate, which may be stationary or moving. This force can be analyzed by using Newton's second law of motion or from the impulse momentum equation also. So coming to the first position, the jet striking a stationary vertical plate. Jet striking a stationary vertical plate. So in the direction of the jet, so consider this is the jet and which is flowing with a velocity v, and this is the stationary plate. The plate is fixed. If the jet of water hits the stationary plate, then the water will convert its direction from x to y direction. So in that case, the force acting in the direction of the jet to the plate can be calculated by using the formula Fx equals to rho a v square. Then the work done acting on the plate is Fx into 0. So therefore the work done is 0. Here rho is the mass density, v is the velocity of the jet, and a is the area of the jet, that is pi d square by 4. Another condition, jet striking a stationary inclined plate. If the plate is inclined and fixed, and if the water is flowing with a jet velocity v, then after hitting the plate, it can convert its direction into y and z direction with a component of with a vertical and horizontal component. So if we take the horizontal and vertical component, then the forces acting on the jet can be calculated by using the formula. The normal force acting on the jet is Fn equals to rho a v square into sine theta. In x direction, Fx can be calculated as Fn into sine theta, the horizontal component Fn sine theta. So it can be written as Fn is rho a v square sine theta. So it can be written as rho a v square sine square theta. And in y direction, Fn cos theta, that will be rho a v square into sine theta cos theta. And here Q2, the discharge Q1 can be calculated as Q1 equals to Q by 2 into 1 plus cos theta. So here theta is taken as obtuse angle side. So obtuse angle side. Then Q2 is nothing but Q by 2 into 1 minus cos theta. And in this case also the work done is 0. Then another one, the jet striking a moving vertical plate. And in this case, the jet does not strike the plate with a velocity v, but it strikes with a relative velocity equal to v minus u. Here v is the jet velocity and u is the moving velocity of the plate. Therefore, the force exerted by the jet on moving plate in the direction of jet Fx is given as rho a into v minus u whole square. The work done per second by the jet on the plate is Fx into u. Here u is the velocity of plate in the direction of jet. So we can write the work done as rho a into v minus u whole square into u. In SI units, rho is 1000 kg per meter cube for water, and work done will be Newton meter per second. And another condition, the jet striking a moving inclined plate. So in this case also we are going to take both the velocities, the velocity of the jet and velocity of the plate V and U. So in this case the normal force Fn is rho A into V minus U whole square sin theta. And if we take horizontal and vertical components, then horizontal component Fx equals to Fn sin theta, that is rho A into V minus U whole square sin square theta. And Fy equals to Fn cos theta in vertical direction by Fy equals to Fn cos theta, that is rho A into V minus U whole square sin theta cos theta. And the work done per second by the jet on the plate is given as Fx into U. Here the equation will be rho A into V minus U whole square into U sin square theta. Then another condition, force exerted by a jet on a stationary curved plate. So in curved plate, again we are going to take three conditions. The first condition is jet strikes the curved plate at the center. If the jet strikes the curved plate at the center, then the water will reflect both in horizontal and vertical direction with its components as horizontal and vertical components. Then if the jet strikes the plate at center, if it is in fixed condition, then Fx will be rho A V square into 1 plus cos theta and Fy will be minus rho A V square into sin theta. Why? Because here the water will goes up and again comes in another direction, so that we get negative direction. The angle of deflection of the jet is 180 minus theta, and in this case the work done is 0. Why? Because the plate is fixed. Another condition, jet strikes the curved plate at one end tangentially when the plate is symmetrical. So here the jet strikes the curved plate at one end tangentially when the plate is symmetrical. So here the water is flowing in tangential direction to the curved plate at one direction. And in this case, the force acting on the plate can be calculated as Fx equals to 2 rho A V square into cos theta, and Fy will be 0. Another third condition is jet strikes the curved plate at one end when the plate is unsymmetrical. So in this case, we can get both x and y direction. So in x direction, the force is rho A V square into cos theta plus cos phi, and in y direction, Fy equals to rho A V square into sin theta minus sin phi. Here theta is the angle made by tangent at inlet tip with x-axis, and phi is the angle made by tangent at outlet tip with x-axis. Then another condition, force on the curved plate when the plate is moving in the direction of the jet. Here the plate is not fixed, it is moving from one place to another plate. So we are getting both the velocities, that is velocity of the jet and velocity of the plate. Therefore the force in x direction Fx equals to rho A into V minus U whole square into 1 plus cos theta. The work done will be rho A into V minus U whole square into U into 1 plus cos theta. Another condition, force exerted by a jet of water on a series of vanes. So if the number of vanes are there and if the jet of water is the water force hitting all the vanes, all the series of vanes, then in that case the force exerted on the plate by the jet can be calculated as rho A V into V minus U. The work done is rho A V into V minus U into U. Here the velocity will also include in it. Then the kinetic energy of jet per second is half rho A V into V square, and the efficiency of the jet is given as 2 into V minus U into U by V square. The condition for maximum efficiency is U equals to V by 2. The maximum efficiency usually for this case is the 50%. Okay, so up to this we will complete 2 topics. We have completed 2 topics, that is principal properties of the fluid and impact of jet. So in the next class we will discuss the remaining. Thank you everyone.